Good day! We are Group Mohon, Team 3 from CE 2101 Group 2, with team members consisting of Batocael, Laga, Murillo, and Villas. A little info of our group name Mohon is that Mohon is a sturdy concrete object permanently placed on the ground to mark positions of a point or boundary corner which has the letters PS engraved in it, which means private survey. So now what we're going to talk about is in continuation of the previous group's materials and discussion on the different types of leveling. The sequence of the topics are as follows: three-wire leveling, curvature and refraction, trigonometric and Stadia leveling, and lastly, the common mistakes or errors found in leveling. This is Patokael speaking, and I'm going to tackle about the three-wire leveling. Three-wire leveling allows the surveyor to immediately verify whether the readings are correct. Thus, three-wire leveling increases precision in leveling. Here is why. Three-wire leveling by definition is a process or method of reading and recording a rod reading for each of the three horizontal crosshairs on each shot, then averaging the readings in agreement with the center reading. All three readings are read to the nearest millimeter. Reading all three wires allows distance determination and refines and checks the backside and the foresight readings. The instrument used for this method includes an automatic level that provides a single consistent line of sight and two nearly identical rods. One could also suffice that are used for the simultaneous observation of the foresight and the backside readings. As the name implies, this method reads three readings. Here, the level reticle pattern contains three horizontal lines. Level rod readings are taken on all three wires on the reticle. The three readings are checked for accuracy in that the differences between the middle and both the top and bottom cross wires should be about the same. Moreover, the difference between the top and bottom should be about twice the half intercepts. This approach to leveling minimizes the possibility of blunders in reading the level rod. This is very helpful in subsequent data reduction when determining whether the sum of the backside and foresight distances were equal throughout the level loop. Before we proceed in filling the table for the three-wire leveling, we have here an image of the setup of the three-wire leveling. So, you may have remembered that the setup is the same as that of the differential leveling. So we can thus say that the three-wire leveling has the same applications, the same processes as that of the differential leveling. However, the differences between the two is that the three-wire leveling reads three crosshair readings, meanwhile the differential leveling reads only one. These are the equations that are to be used on the next few slides. As for the Stadia, it is the sum of the differences of the upper reading and the lower reading, the mean, the average of the three values, the elevation, which is the difference between the height of the instrument and the mean of the foresight mean reading, and the height of the instrument equates to the elevation value plus the mean of the backside mean reading. Here we have an empty table. So these are the crosshair readings for the corresponding benchmarks and turning points. To get the mean, we have to get the average of these three values. Add this all up and divide by 3, we get 0.935. Add this all up and divide by 3, we get 0.899. To get the Stadia, we have to get the difference between the upper reading and the lower reading. So this is A, B, C. A minus B, B minus C. And add the differences together. So from this A minus B, we get 0.217. From this B minus C, we get 0.217. Add those two values, we get 0.434. A minus B and B minus C, add the two values, we get 0.435. To get the height of the instrument value, we have here an initial leveling elevation value. So add this value with the mean reading from the backside, and we get 445.177. To get the next elevation value, we need the height of the instrument value and subtract it with the mean reading from the foresight. So we have 444.278. Again, do the process, get the average from these three values, get the average of these three values, and we get these corresponding values. The stadia is the sum of the differences between A minus B and B minus C. Here are the corresponding values then. And as for the HI value, we need this previous elevation value and add it with the mean reading from the backside. And as for the elevation value, we need the value from the HI and subtract it with the mean reading from the foresight. We have to do this process over and over again until we get to the benchmark 2. The benchmark 2 should equate to 445.126. Once all the computations are done, we need to do an arithmetic check. Arithmetic check is done to conclude errors from the table. We have to take the summation of the means in both the backside and the foresight, and the elevation, and add it all up. So the summation of the backside mean reading is 7.620. The summation of the foresight mean reading is 6.736. Note that the foresight is denoted by negative sign. So as mentioned, this is the formula: the elevation of the benchmark 1, the summation of backside, the summation of foresight. Equate it to the benchmark 2. These elements are then replaced with the corresponding values and then compute. If the values are the same on both ends, then we can conclude that the arithmetic check is done successfully. That is all for three-wire leveling, and the next topic is...
Hello, my name is Miko Murillo, and I will be discussing curvature and refraction. In engineering, the effects of Earth curvature and refraction of the line of sight must be considered for long sights and proper leveling work. Curvature causes the points to appear lower than they are, while refraction causes them to appear higher. So we all know that the flat Earth theory is false, right? And we all know that the Earth is a sphere and everything is intact due to gravity. Earth has a curved face which is assumed to be a level surface, but the line of sight as furnished by the leveling instrument is horizontal and not the level line. Therefore, all points on the line of sight are not equidistant from the surface of the Earth, and consequently, the points read on the staff are not strictly at the same level as horizontal hair of the diagram. The level line falls away from the horizontal line of sight, and the vertical distance between the horizontal line and the level line denotes the effect of curvature of the Earth. So as you can see here on the figure, A prime is the instrument station and P is the point where the staff is held. On looking through the telescope, we sight along AB, the horizontal line of sight, and take the staff reading PB. The point B is considered to be at the same level as A, but actually the points C and A are at the same level. The true reading therefore is PC. So here on the next figure, D is the length of the sight or the distance from the instruments to the staff station in kilometers. BC is the error due to curvature. O is the center of the earth, and R is the radius of the earth. So by geometry, BC times BE is equals to BA squared. Since BC is usually very small and as compared with the diameter of the earth, and its square will still be much smaller and may therefore be neglected in calculation. So BC times CE is equals to BA squared, and the taxing diameter of the earth as 12,742 kilometers, we get BC is equals to D squared over the taxing diameter of the earth, which is 12,742 kilometers. So if we solve this in meters, we multiply D squared with 1,000 and divide it to 12,742. So the error in staff reading due to curvature of the earth is 0.0785 D squared meters, where D is the distance from the level to the staff in kilometers. So now that we have done discussing curvature and its error leading to surveying, next we'll be discussing refraction. Refraction is a well-established law of physics that rays of light passing through layers of different densities do not remain straight but are refracted or bent down towards the denser medium. Consequently, the ray of light from the staff to the instrument is not straight as AB in our figure below, but it follows a curved path AD concave towards the earth. As they near the surface of the earth, it is denser than the upper layers of air. Under normal conditions, arc AD may be taken as circular and of radius 7 times that of the earth. The effect of refraction is therefore 1 over 7 or 7th of that of the curvature, but is of opposite nature. Hence, the correction of refraction is additive to the staff reading. So the error due to refraction is BD is equals to 1/7 of line BC. So if we use the error of curvature, which is 0.0785 D squared, if we divide it by 1/7, we get 0.0112 D squared meters. So now we'll be talking about the combined correction due to curvature and refraction. Since the effect of curvature is to increase the staff readings and the effect of refraction is to decrease them, also the effect of curvature is greater than that of refraction. The combined effect is therefore to increase the staff readings. Hence, the combined correction is subjective. So, the combined error due to curvature and refraction is CD is equals to BC minus BD. So, BC minus 1/7 of BC is equals to 6/7 of BC. So, 6/7 of the error of curvature, which is 0.0785 D squared, is equals to 0.0675 D squared meters. So this is the combined formula for curvature and refraction. So guys, take note of this formula. So guys, we'll be using this formula, which is D is equals to 3.57 square root of H. So to get so we are looking for the height of the lighthouse, which is the H. So in order to isolate H, we need to multiply both sides by the power of 2 so that the square root will be cancelled. And then our formula will be D squared is equals to 3.57 squared H. So let's isolate H. So H will be equals to D squared over 3.57 squared. So we all know that D is 24.14 kilometers. So if we do that, so 24.14 squared divided by 3.57 squared, we have our lighthouse will be 45.72 meters. So yeah, that's it. And let's move on to the other topic, which will be discussed by Kerman Jude Laga.
Good morning, everyone. I'm Kerman Jude Laga, and I will talk about trigonometric and Stadia leveling. First, what is trigonometric leveling? Trigonometric leveling is the process of determining the different elevation of the station from observed vertical angle and horizontal distance. The vertical angle is measured via theodolite, while the horizontal distance may either be measured or calculated. It is most commonly used in steep and rugged terrain or when the survey points are inaccessible. The instruments that is most commonly used in trigonometric leveling are the theodolite or the total station and the range poles. So, how do we do trigonometric leveling? First, we take the observation of the vertical angles via a theodolite or a total station and then compute the distances using them. If the distances are large enough, then we have to provide the correction for the curvature and refraction that we provide to the linearity to the distances that we have computed. So how do we compute for the distances? We first need to remember some terms or legends that will be vital in computing. HI stands for height of the instrument above point A. R stands for rod reading at point B when the vertical angle is read. S stands for the hypotenuse, H stands for the horizontal length, and V stands for the vertical height. So now let's go to the computations. While referring to the diagram to the left, if S and the vertical angles are determined, V is equals to S sine alpha or V is equals to S cosine Z. If H and the vertical angles are determined, V is equals to H tan alpha or V is equals to H tan Z. The change in elevation between points A and B or delta elevation is equal to HI plus V minus R. Do remember, if R is made equal to the HI, then the two values cancel and the computations are simplified. These equations are applicable when shots are taken at less than 1,000 feet. For shots longer than 1,000 feet, the effects of curvature and refraction must be taken into account. So now let us go to the shots longer than 1,000 feet, otherwise known as long lines. Assuming long sights are involved, the difference in elevation between points A and B would then be written as delta elev is equal to HI plus V minus R plus 0.0675 multiplied to the square of H over 1000. The effects of curvature and refraction can then be eliminated if the vertical angle observations are made simultaneously at both ends of the line, such as at point A and B. This technique is termed as reciprocal and vertical angle observation. When applied, it is no longer necessary to take into account the effects of curvature and refraction, and the correct difference in elevation between 2 points is taken as the mean of the two values computed both ways. Thus, delta LF is equals to h over 2 multiplied to tan alpha plus tan beta, or delta LF is equals to s over 2 multiplied to tan alpha plus tan beta, wherein alpha is vertical angle taken from A to B, and beta is the vertical angle taken from B to A. And now let us go to Stadia leveling. Stadia leveling, also known as tachyometric surveying, is a modified form of trigonometric leveling in which the tachyometer principle is used to determine the elevation of a point. In this case, the line of sight is inclined from the horizontal. It is more accurate and suitable for surveying in hilly areas. When the ground is rough and more observations at a faster rate with ordinary precision are acceptable, it is when the Stadia leveling is the choice. Observations are made on a Stadia rod, usually a level staff but with a larger least count of 1 cm, and horizontal as well as vertical distances are computed from these observed readings. And now, let's focus on the figure in this slide. In this type of situation, the computations are done using the similar triangles of the figure, in which d over f is equals to s over I, or d is equals to f over I multiplied to L, which is equal to k times s. Thus, d is equals to ks plus c, in which the uppercase f is equals to the principal focus, the lowercase f is the focal length, O stands for the optical center, I stands for the distance between the stadia hairs, C stands for the distance from the optical center to the center of the instrument, S stands for the stadia interval or the intercept, and K is equals to I, f over I is equals to is the stadia interval factor. And now let's us focus on the next figure, which is on this slide. The computations are done using the similar triangles of the figure in this slide, wherein VD is equals to Ks cosine alpha multiplied to sine alpha plus C sine alpha, which can also be DE equals to RRB minus VDB plus VDR minus RR lowercase r, wherein VD is the vertical distance, K is the stadia interval factor, S is the stadia intercept, and C is the distance from the center of the instrument up to the principal focus, which is 0 for internal focusing telescope. DE is the difference in elevation, and RR is the rod reading. And that is all for the trigonometric and stadia leveling.
For the last part of our report, we are going to discuss the following common errors and mistakes in leveling and what we can do with them. These are the following. First is misreading the rod, second is incorrect recording, third one is erroneous computations, fourth one, rod not fully extended, fifth one is moving to points. The first one is misreading the rod. This mistake most frequently occurs when the line of sight to the rod is partially obstructed by vegetation or other objects in the field. An example would be this image. Due to the objects that may block the view, recording the measurements can be mistakenly taken. To avoid this from happening, one of the members of the party can clear a small portion of the area. Second one is incorrect recording. In leveling, there are a lot of numbers to be written down. To lessen these errors, the recorder should understand the leveling process, call out the readings as he records them in order to prevent the recording of incorrect values, and to be able to visualize the operation for which he makes his recordings. An example with this error is recording 3.54 instead of 4.54. The third one is erroneous computation. Although level notes only require simple additions and subtractions, mistakes in these computations are still committed. For this reason, mathematical checks should always be performed to ensure that only correct values are determined. The next one is when the rod is not fully extended. Rods are compacted to make it easy to carry. When not extended properly, it will cause a wrong recording. It is important that it is fully extended when reading the high and or long rod. The two sliding sections should lock properly into position. The clamp should also be tightened firmly to avoid the upper portion of the rod from sliding downward. The last mistake in leveling is moving the turning points. This mistake could be prevented by using only stable and clearly defined turning points or by marking the position of the rod with paint, lumber crayon, or chalk.
Thank you for listening, and we hope that all of you have enjoyed learning about leveling.